When you write data to a system, you rely on a transaction block to keep that data intact. The theoretical gold standard for this integrity is a property called serializability. It guarantees that even if thousands of transactions hit the database at the exact same millisecond, look at these data streams. Under true serializability, when multiple transactions compete for the same resource, they collide. The system forces them to queue up. Parallel execution drops to zero, and the database grinds to a halt to process them one by one. Look at this breakdown of 18 major databases from researcher Peter Bayless. Only 3 provide serializability by default. Look at the heavyweights. Oracle defaults to snapshot isolation, Postgres to read committed, and MySQL to repeatable read. To handle internet-scale traffic without stalling, these database vendors silently drop serializability. Instead, they run on what are known as weak isolation models. True sequential execution is a theoretical luxury. Without realizing it, most back-end engineers are actively trading away strict mathematical consistency just to keep their system throughput high. The specifications mapping out these weak isolation levels were formalized in the 1992 ANSI SQL standard, but that standard has a major flaw. It was written for older lock-based systems. It is ambiguous, and it completely fails to account for how modern databases actually implement multi-version concurrency. This leads to a dangerous architectural blind spot. If you execute the exact same read-committed SQL command on 2 different database engines, you will often get completely different data snapshots returned to your application. Specific engine-level retry logic makes this divergence a mechanical reality for production systems. Back-end developers who rely purely on standard SQL syntax without understanding the concurrency mechanics of the engine underneath it are actively risking silent data corruption. To understand why engines diverge, you have to look at how they handle conflicts. The legacy method is pessimistic control, specifically a protocol called two-phase locking. As we see in this diagram, two-phase locking works by placing hard restrictions on data rows. When transaction A accesses a block, it spawns a lock. When transaction B tries to read or write to that same block, it hits a wall and stops entirely. At scale, this creates massive operational friction. Transactions queue up, deadlocks multiply, and overall throughput degrades heavily. The modern architectural response to this blocking problem is multi-version concurrency control, or MVCC. Here is how MVCC changes the mechanics. When transaction A updates a block, it does not overwrite the data. Instead, it creates a duplicate version stamped with a new transaction ID. The original block remains perfectly intact and visible to transaction B. This establishes the core rule of MVCC. Readers do not block writers, and writers do not block readers. But that lack of friction comes with a trade-off. By eliminating pessimistic locks, MVCC exposes transactions to the risk of reading overlapping or outdated snapshots if the database's isolation rules aren't rigidly defined. Engineers map these risks using a matrix of isolation levels against specific concurrency anomalies. Take read-committed isolation, the default for systems like PostgreSQL. By definition, it guarantees that a transaction will only read data that has been successfully committed, preventing what is known as a dirty read. Look at this anomaly matrix. While read committed prevents dirty reads, it intentionally leaves the door open for 2 dangerous anomalies: lost updates and write skews. We can see the impact of a lost update in high-contention e-commerce drops, like the chaos surrounding the PlayStation 5 release on Costco's website. Thousands of users hit the database simultaneously. 2 concurrent transactions read the exact same stock value. They both decrement the inventory in memory and write back to the database. One write silently overwrites the other, effectively deleting a valid purchase and overselling the console. Write skews carry even higher stakes. In 2014, an attacker exploited a write skew anomaly to bankrupt the Flexcoin cryptocurrency exchange. The attacker flooded the exchange with concurrent, non-transactional read-modify writes. Because the system ran on weak isolation, the attacker tricked the database into validating multiple withdrawals against the exact same outdated account balance. Weak isolation actively transfers the burden of concurrency management away from the database layer. It places that burden directly onto the application logic, where a subtle timing error can instantly become a fatal exploit. To prove how engine architecture alters data reality, let's see how 2 different databases handle an identical read-committed collision. We will start with Postgres. Imagine an initial state where transaction A updates a specific row. Milliseconds later, transaction B attempts to update that exact same row using a where clause. This visualization shows the collision. Point 2, running transaction B, recognizes the conflict. Its update statement pauses and enters a wait state while transaction A finishes its commit. Here is what Postgres does next. To resolve the serialization error, it does not retry the entire statement. It only retries the specific conflicting row against the newest version of the data. This row-level retry has a strict mathematical consequence. Transaction B's where clause evaluates the new version of that single conflicting row. But as we see in this output table, it completely ignores any newly inserted rows that transaction A just added. This means Postgres just processed a single SQL statement using an inconsistent split snapshot of the database. The non-conflicting rows were evaluated at the original snapshot time, but the single conflicting row was evaluated later at the new. By resolving serialization errors internally, it hides the concurrency friction from the application layer entirely. Now let's shift this exact scenario to UgiByteDB to see how distributed databases architecturally diverge from single-node systems. When UgiByteDB hits that same write conflict, it takes a different mechanical path. Instead of a row-level retry, it undoes the entire statement and reverts back to its initial state. Because it executes a statement-level retry, UgiByteDB reruns the entire command. It pulls a completely fresh, unified snapshot of the database, pushing transaction B's read point forward in time to include everything transaction A just did. Look at the final output for UgiByteDB. Because it uses a unified snapshot, transaction B's where clause now catches the updated rows and the newly inserted rows from transaction A. This directly contradicts the output we just saw in Postgres. Submitting the exact same read committed SQL command yields distinct data outputs, depending entirely on whether the engine utilizes row-level or statement-level retries. If we pull back from the internal database mechanics and look at the larger distributed system architecture, the problem becomes clear. Treating ANSI SQL isolation definitions as a universal source of truth across different vendors is a massive liability. The sheer scale of modern internet traffic and the high contention found in microservice architectures aggressively amplify these underlying engine differences. This creates an absolute mandate for back-end developers. Application logic must be explicitly built to defend against the specific anomalies that their chosen database engine permits. You have to implement optimistic concurrency validation at the application layer, utilize explicit select for update locks to handle contention, or mathematically force serializable isolation for your most critical transactions. Database engines are opaque systems with individual quirks. Treating standard SQL as a guarantee of universal behavior is a primary vector for modern data corruption.